Deep in the industrial heartland of Russia, where the Ural Mountains slice through the continent to divide Europe from Asia, lies a sprawling mechanical organism that defies conventional description. This is not merely a factory in the traditional sense, but rather a self-contained industrial city-state, a fortress of production that occupies over 827,000 square meters of manufacturing floor space. This is Uralvagonzavod, the Ural Railroad car factory located in the closed and gritty city of Nizhny Tagil. To understand the scale of this place, you must strip away any preconceived notions of modern, sterile assembly lines found in Silicon Valley or high-end German automotive plants. Imagine instead a place that feels like the inside of a living, breathing volcano, where the air tastes of sulfur and iron dust, and where the ground perpetually trembles under the rhythmic pounding of hydraulic presses capable of exerting force equivalent to stacking 3 Eiffel Towers on a single dinner plate. It is a place where the temperature differential between the molten steel inside and the Siberian winter outside can exceed 1,600 degrees Celsius, creating a thermodynamic war zone that stresses both metal and flesh to their absolute breaking points. The history of this facility is written in the frozen soil of the 1940s, born from a desperate evacuation during the Second World War when the Soviet Union physically ripped its industrial base out of the ground in Ukraine and Western Russia to move it beyond the reach of the Luftwaffe. They transported entire factories, bolt by bolt, across thousands of kilometers of snow-covered tracks to reassemble them here in the geological shield of the Urals. That legacy of desperation and sheer brute force remains baked into the walls of the current facility. It was here that the legendary T-34 was churned out in numbers that overwhelmed the technological superiority of the German panzer divisions. And it is here today that the Russian Federation continues to manufacture its main battle tanks, including the T-72B3 and the T-90M Prorив. The layout of the plant is a chaotic masterpiece of Soviet central planning, a labyrinth of rail spurs, open hearth furnaces, and assembly halls so vast that workers use bicycles and buses to navigate between departments. If detailed technical breakdowns of heavy industrial engineering and extreme manufacturing interest you, subscribe. I have got more of these coming. To stand at the gates of Uralvagonzavod is to witness the collision of the unstoppable force of industrial output and the immovable object of the Russian winter. The sheer logistics required to keep this facility running are staggering, consuming as much electricity annually as a mid-sized European city, and devouring water at a rate that requires dedicated diversion channels from local reservoirs. The raw materials arrive by the trainload, endless lines of flat cars carrying iron ore, coal, manganese, and scrap metal, all destined to be fed into the insatiable maw of the foundry. This is the beginning of the tank's life, not on a computer screen, but in the violent, chaotic environment of the melt shop. Here, the primary objective is to create steel that is hard enough to shatter a kinetic energy penetrator moving at 1,700 meters per second, yet ductile enough not to crack under the shock of a high explosive impact. This metallurgical paradox requires a specific recipe of alloying elements, chromium, nickel, and molybdenum, mixed with a precision that belies the primitive violence of the furnace itself. The atmosphere inside the foundry is heavy, oppressive, and thick with a haze that obscures the high ceilings, where overhead cranes, looking like prehistoric predatory birds, slide back and forth on blackened rails. The sound is not just noise, it is a physical pressure that pushes against your chest, a low-frequency rumble punctuated by the screech of metal on metal and the sudden thunderous crack of an electric arc striking the scrap pile. It smells of ozone, burnt sand, and the distinct metallic tang of hot copper, a sensory assault that signals the presence of energies far beyond the human scale. There is a sense of ancient magic here, a feeling that the workers, clad in thick, fire-resistant wool and heavy leather aprons, are not just technicians, but alchemists coaxing a demon out of the rock. The process of casting the turret for a tank like the T-90 represents one of the most difficult challenges in heavy manufacturing. Unlike Western tanks such as the American Abrams or the German Leopard 2, which use large, flat plates of welded armor to form a boxy turret, Russian design philosophy has traditionally favored a rounded cast turret for better ballistic deflection and a lower profile. To achieve this, the foundry must create a massive sand mold, a negative space that defines the complex geometry of the turret's exterior and interior. Imagine trying to bake a cake where the batter is liquid steel at 1,550 degrees Celsius, and the pan is made of compressed silica sand and chemical binders. If the sand is too wet, the steam generated by the molten metal will cause an explosion that can level the building. If the sand is too dry, the mold will crumble, ruining a casting worth hundreds of thousands of dollars. The molten steel is poured from a ladle the size of a small house, tipped by a crane operator sitting in a cab 50 feet above the floor, guiding the stream of liquid fire into a spruce no wider than a dinner plate. Once the metal is poured, the physics of cooling take over, and this is where the unseen battle for quality is fought. Steel shrinks as it cools, and if it cools unevenly, it creates internal voids and stress fractures, microscopic weaknesses that would prove fatal on the battlefield. To prevent this, the engineers use a system of risers and chills, sacrificial reservoirs of molten metal that feed the casting as it shrinks, ensuring the turret remains solid throughout. It takes days for a casting of this mass to cool sufficiently to be broken out of the mold. The breakout area is a scene of violent excavation where massive vibratory shakers pulverize the sand mold, revealing the rough gray steel of the turret beneath. It looks organic, like a fossil unearthed from the bedrock, covered in flash and sprues that must be cut away with torches and ground down with industrial abrasives. Now, step away from the inferno of the foundry for a moment and let the silence of the cooling yard wash over you. Here, the massive castings sit in rows under the gray sky, aging like fine wine. This is not poetic license. The steel needs to rest to allow the residual internal stresses from the casting process to normalize. Snow accumulates on the rough metal shoulders of the turrets, melting only where the deep heat of the core still radiates outward, creating little halos of steam in the freezing air. It is a graveyard of potential violence, silent and cold, waiting for the next stage of its transformation. The contrast is jarring. Moments ago, the air was screaming with the sound of arc furnaces. Now the only sound is the crunch of boots on gravel and the distant, mournful whistle of a shunting locomotive moving another load of coal to the power plant. Moving from the foundry to the hull shop, the manufacturing philosophy shifts from the organic art of casting to the brutal precision of forging and welding. The hull of a modern main battle tank is constructed from rolled homogeneous armor, or RHA, plates that are incredibly dense and heavy. To visualize this, imagine a sheet of plywood, but instead of wood, it is high-hardness steel, and it is 80 to 100 millimeters thick. These plates are not cut with saws. They are sliced with high-definition plasma torches or submerged in water and cut with high-pressure abrasive jets to prevent heat from altering the temper of the steel near the cut edges. The hull is essentially a V-shaped tub designed to deflect the blast of anti-tank mines away from the crew compartment. Assembling this tub requires welding thick plates together, a task that demands a completely different set of skills and machinery than the casting process. In the welding halls of Urals, you will not see rows of men with handheld stingers creating bead after bead. The scale is simply too massive for manual labor alone. Instead, the factory utilizes massive gantry systems equipped with automatic submerged arc welding heads. In this process, the welding arc is completely buried under a layer of granular flux, a material that looks like coarse sand, which melts to form a protective slag over the molten weld pool. This prevents the oxygen in the atmosphere from contaminating the steel, which would cause porosity and weakness. Think of it like sewing two pieces of fabric together, but the needle is an electric arc hotter than the surface of the sun, and the thread is a continuously fed wire of alloy steel. The machine moves with a hypnotic, steady hum, laying down a perfect, continuous seam of metal that fuses the armor plates into a single, monolithic structure. The stakes here are incredibly high because a bad weld is not just a cosmetic defect. It is a structural failure point that could cause the tank to split open if hit by a kinetic round. Every centimeter of these critical welds is inspected using X-ray and ultrasonic testing equipment, looking for microscopic cracks or inclusions that the human eye cannot see. If a defect is found, the entire section must be gouged out with carbon arc torches and re-welded, a costly and time-consuming penance for failure. The hull shop is a place of sharp angles and blue light, where the air is filled with the fine metallic dust of grinding and the acrid smell of ozone generated by the high-voltage welding equipment. Leaving the welding hall, you enter a corridor that seems to stretch on forever, a transition zone where the temperature drops and the air clears. The floor here is worn smooth by decades of boots and tires, the concrete polished to a dull sheen by the passage of millions of shifts. You can hear the distant clanking of the assembly line, a rhythmic mechanical heartbeat that grows louder with every step. There is a sense of anticipation here, the feeling of moving from the creation of raw components to the assembly of a complex machine. It is a breathing space, a moment to reset your senses before plunging into the intricate chaos of the final assembly hall. The assembly line at Uralvagonzavod is a relic of the Soviet obsession with mass production, a concept known as tankograd. Unlike Western manufacturers who might build tanks in stationary bays, moving crews from one hull to the next, Uralvagonzavod utilizes a moving conveyor system for much of the process. This is the industrial equivalent of a river, a slow-moving stream of steel that flows through the factory, accumulating parts and complexity as it goes. The hull, now a painted green tub, is mounted on a dolly and pulled along the track. The first major installation is the suspension system, torsion bars. A torsion bar is essentially a long, high-strength steel spring that runs across the width of the hull floor. When the tank's road wheel hits a bump, the arm twists this bar, absorbing the energy. Installing them requires massive hydraulic rams to pre-tension the bars, storing potential energy that will later support the 50-ton weight of the vehicle. It is like winding the spring of a giant deadly watch. Then comes the heart of the beast, the engine. For the T-72 and T-90 series, this is typically a V92S2 diesel engine, a 12-cylinder monster that produces over 1,000 horsepower. This engine is a direct descendant of the V2 engine that powered the T-34 in World War II, a testament to the Russian philosophy of evolutionary rather than revolutionary engineering. It is compact, reliable, and designed to run on almost any combustible liquid, from high-grade diesel to kerosene or even benzene in an emergency. Lowering this massive block of iron and aluminum into the tight confines of the engine bay is a delicate ballet performed by overhead cranes. The tolerances are tight, measured in millimeters, and the mechanics must guide the engine onto its mounts with pry bars and gloved hands, connecting fuel lines, coolant hoses, and the complex transmission system that transfers power to the drive sprockets. The transmission of a tank is not like the transmission in your car. It does not just change gears, it steers the vehicle. By varying the speed of the tracks on either side, the transmission allows the tank to turn, spin in place, or drive straight. This system involves massive planetary gear sets and hydraulic clutches, all of which must be aligned perfectly within the hull. A misalignment here means the tank will throw a track in the field, turning a mobile fortress into a stationary pillbox. Knowing what you now know about its real-world production bottlenecks and extreme hazards, do you think the massive capital investment in this facility was worth it? Share your thoughts below. The assembly hall is a cacophony of pneumatic wrenches, shouting foremen, and the high-pitched whine of electric hoists. It smells of grease, diesel fuel, and fresh paint. This is where the machine starts to look like a tank. The road wheels, large aluminum and steel discs rimmed with rubber, are bolted onto the suspension arms. The tracks, heavy chains of steel links, are laid out on the floor, and the hull is lowered onto them. Connecting the tracks is a brutal job, requiring workers to use sledgehammers and crowbars to pull the heavy links together and insert the steel pins that hold them in place. It is physical, back-breaking labor that has changed little in 80 years. One of the most controversial and distinct features of these Russian tanks is the autoloader. While Western tanks typically rely on a human loader to shove shells into the breech, the T-series tanks use an electromechanical carousel located in the floor of the turret basket. This mechanism holds the propellant charges and the projectiles separately. When the gunner selects a round, the carousel spins to the correct slot. A mechanical arm grabs the projectile and propellant and rams them into the gun breech. This allows the tank to be smaller and lighter, with a crew of only 3 instead of 4. However, it also places a massive magazine of high explosives right beneath the crew's feet. Watching the autoloader being installed is like watching the assembly of a giant lethal clock mechanism. It is a dense cluster of servos, gears, and sensors that must work flawlessly amidst the violent recoil of the main gun. The marriage of the turret to the hull is the crowning moment of the assembly process. The fully equipped turret, sporting its 125mm smoothbore gun, is lifted high into the air. This gun, the 2A46M, is capable of firing armor-piercing, fin-stabilized discarding Sabre rounds, guided missiles, and high-explosive fragmentation shells. The crane operator lowers the turret slowly, the massive ring gear on the bottom of the turret aligning with the race on the hull. This is a precision fit. The turret must be able to rotate 360 degrees in seconds, regardless of the tank's angle or the weather conditions. Once seated, the connection represents the final integration of firepower and mobility. Let us pause for a moment to appreciate the human element in this industrial leviathan. The workers of Uralvagonzavod are often 3rd or 4th generation employees. Their grandfathers built T-34s, their fathers built T-62s, and now they build T-90s. The factory is the gravitational center of their lives, providing housing, heating, and social structure. It is a monotown mentality, where the fate of the city is inextricably linked to the orders coming from the Ministry of Defense. The cafeteria serves thousands of meals a day, simple, hearty food designed to fuel hard labor in a cold climate. In the locker rooms, the air is thick with the smell of sweat and industrial soap, a testament to the sheer physical exertion required to birth these machines. Operational reality at Uralvagonzavod also involves a logistical nightmare that is almost impossible to comprehend without seeing it. The factory consumes raw materials at a rate that requires a constant stream of rail traffic. If the rail lines freeze or a switch fails, the entire production line can grind to a halt within hours. The just-in-time delivery methods of Toyota or Apple would fail miserably here. Instead, the factory relies on massive stockpiles of ore, coal, and steel plate, mountains of material that act as a buffer against the unpredictability of the Russian supply chain. This requires acres of storage yards, massive gantry cranes to move the stockpiles, and a small army of logistics coordinators who track every ton of material. Furthermore, the facility creates its own weather. The heat generated by the foundries and the power plant is so intense that it creates a microclimate around the industrial zone. Snow melts faster here, the fog is thicker, and the thermal updrafts can be felt by pilots flying overhead. This waste heat is not entirely wasted. It is piped into the residential districts of Nizhny Tagil, heating the apartment blocks where the workers live. It is a symbiotic relationship. The workers keep the factory alive, and the factory keeps the workers from freezing to death. This integration of life and industry is a hallmark of the Soviet legacy that still permeates the operation. The testing phase is where the rubber, or rather the steel track, meets the road. Before a tank is accepted by the military, it must survive the proving grounds. Just outside the factory gates lies a torture track designed to break machinery. It consists of deep mud pits, concrete obstacles, vertical walls, and trench crossings. The new tanks are driven straight from the assembly line into this mud. Test drivers, often veterans with nerves of steel, push the 60-ton vehicles to their limits, revving the V12 engines until they scream, slamming the suspension over concrete bumps at 40 kilometers per hour, and slewing the tanks through waist-deep slurry to test the watertight seals. It is a violent, dirty spectacle. The tanks roar and belch black smoke, their tracks churning the earth into a thick paste. The goal is to find failures here, in the shadow of the factory, rather than on the battlefield. If a seal leaks, it is fixed. If a track pin snaps, the batch is inspected. If the stabilizer on the main gun drifts, the electronics are recalibrated. This is the final exam, and it is graded on a pass/fail basis. The visuals are striking. Pristine, green-painted war machines rapidly becoming coated in the gray clay of the Urals, a baptism of dirt that signifies their transition from product to weapon. Comparing the output of Urovo-Gonzavod to Western competitors reveals a fundamental difference in philosophy. A Western tank factory might produce a few dozen tanks a year, each one a handcrafted masterpiece of technology, costing $10 to $15 million. Urovo-Gonzavod is designed for war of attrition. Its tooling, its layout, and its workforce are optimized for volume. While the fit and finish might not match a German factory, you might see rough weld beads or tool marks on non-critical surfaces. The ruggedness is undeniable. The T-90 is designed to be fixed in a muddy field with a hammer and a wrench, not requiring a diagnostic laptop and a clean room. This good enough philosophy is not a compromise. It is a strategic choice born from the lessons of the Eastern Front, where quantity often has a quality all its own. However, this legacy is a double-edged sword. The factory is filled with aging machinery, some of it dating back to the Cold War or even earlier. Keeping these ancient hydraulic presses and lathes operational requires a constant effort of maintenance and cannibalization. There are modern CNC machines from Europe and Asia interspersed with Soviet-era giants, a patchwork of technology that reflects the geopolitical history of modern Russia. Sanctions and trade restrictions have made it harder to acquire advanced tooling and electronics, forcing the engineers to innovate or regress, finding domestic solutions to replace imported components. This struggle is visible on the factory floor, where the old and the new exist in an uneasy truce. In recent years, the factory has faced the challenge of producing the T-14 Armata, a next-generation tank with an unmanned turret and an armored crew capsule. This design is a radical departure from the T-72 lineage and requires much tighter manufacturing tolerances and more advanced electronics. The struggle to mass-produce the Armata highlights the limitations of the existing infrastructure. The foundry and assembly lines, optimized for the brute simplicity of the older models, struggle with the precision required for the new beast. It is a clash between the inertia of a century of heavy industrial tradition and the demands of 21st century warfare. The environmental impact of such a facility is, predictably, immense. The snow around Nizhny Tagil often has a gray or orange tint from the particulate matter in the air. The soil is enriched with heavy metals. While modern filtration systems have been installed, the sheer scale of the operation makes zero emissions an impossible dream. For the locals, this pollution is the smell of money, the scent of stability. A clean sky would mean the factory has closed, and for a monotown, that is a fate worse than smog. It is a stark reminder that industrial power always comes with a cost, paid for by the environment and the health of the people who sustain it. As we assess the legacy of Uralvagonzavod, we must look beyond the politics of the conflicts its products fight in. From an engineering and historical perspective, the facility is a monument to human tenacity. It is a place where raw geology is transmuted into mechanized armor through the application of fire, pressure, and sweat. It represents a continuity of industrial might that survived the fall of the Tsar, the Great Patriotic War, the collapse of the Soviet Union, and the economic turbulence of the 1990s. It is a survivor, a leviathan that refuses to die, fueled by the necessity of national defense and the sheer momentum of its own existence. The tanks that roll out of these gates will serve for decades, often ending up in conflicts thousands of miles away, in deserts and jungles, far removed from the frozen taiga of their birth. They are the physical embodiment of a manufacturing philosophy that prioritizes durability, simplicity, and mass over elegance and precision. Whether you view them as instruments of aggression or tools of defense, you cannot deny the engineering prowess required to build them at this scale, in this climate, under these conditions. Ultimately, Uralvagonzavod is more than just a factory. It is a testament to the industrial age, a roaring, smoking, grinding reminder of a time when national power was measured in tons of steel poured and kilowatts consumed. It is a dinosaur in a digital world, but a dinosaur with very sharp teeth and thick skin. As long as there is a demand for heavy armor, the fires of Nizhny Tagil will continue to burn, casting their orange glow against the white canvas of the Russian winter, a beating heart of iron in a land of snow. If you found this analysis useful, a like helps more people discover these deep dives. Thanks for watching.